tekniken fungerar.
Jo, det fungerar bra. Så att,
Det är bra.
Jag är ju lite äldre än dig. Nej, men jag använder ju själv. Inte varje månad, men jag använder min dator och kör. Då vet jag att allting går direkt. Så det är lite bra.
Men det finns ju faktiskt en anledning hos Jeps att inte använda PowerPoint. Och det är ju att de är inte fast installerat. Man måste gå upp till 20:e våning. Och ibland hittar man ingen equipment.
Det är också ett jätteproblem.
Ja, det tar så mycket tid.
Så att, men jag ser fram emot det.
You close the door? Oh, yeah. Shall we start? Shall I start?
Yeah, it's just a couple of minutes early, but I think we can start. So.
Yeah. Okay. Okay. Thanks for coming. Thanks for showing interest in this lecture and this topic. I noticed we have a very strong competition from the other lecture hall, and Susan Hansson suggested not to have structural equation modeling on my slide. So therefore I decided to have SEM, only for the specialist, and the other might wonder what it is, and they might become curious and then come, but it didn't really help. You might notice I slightly changed now I write structural equation modeling, truly Swedish innovation, and you see in the title it was a truly Swedish invention. Actually, I thought quite a while about whether it was an invention or an innovation. And now finally I decided it was an innovation. So I put the innovation here. And hopefully later on you will agree with me that it was an innovation. So Andreas Stephan is my name. I'm professor of economics. I will a little bit also talk about international business innovation entrepreneurship. That is the fields where I got my professorship in, but actually I'm now working in accounting and finance, interestingly. So I could add those two fields here. So that will give you some other Swedish innovations. I will hopefully explain you, giving these examples, what is the difference between innovation and invention. You will, maybe that is too much what I promise here to you. At least you will maybe understand what the structural equation model is about. Of course, just for structural equation model, we would need several lectures to understand really what it is, what you can do with it to apply it. Then I mean, at least those of you who have worked with the structural equation model, they have maybe not thought of why is this really a Swedish thing, Swedish invention or innovation, and maybe also that's more for the people really interested in that, what do I think, how will structural equation modeling develop in the future? And then I also have some final reflections. That's all need to watch the time. This is, now I start a little bit with international business here, because this is Michael Porter's so-called diamond model. Michael Porter is a very famous professor at Harvard Business School in strategy and international business, and he has framed the so-called diamond model, actually where he somehow tries to predict the Silicon, or describe, give a theoretical framework for the Silicon Valley phenomenon. why do all these firms locate together? Why does it create locational advantage? And he looks at these different things, internal things in the firm, external things, location factors, factor conditions at the locations, but also the presence of related and supporting industry. And another very important element, actually, that the coexistence of competing firms in the same location. Actually, according to Paul, this is very good. It's very good stimulus. That if very good firms are located close to each other, they can observe each other and they can learn and they encourage each other to become better. I showed this slide about 3 years ago when I got invitation for interview. I showed not this. This was just the introduction, and then I showed our model, how we adopted this framework to our own model in an empirical study. Now I will show you something like how we developed path model, giving this general framework. So what we want to do in this study is to see, can we somehow predict firm performance, giving locational conditions where the firms are located. We use a sample of East German companies for doing so. So basically what we look both at the center is the innovativeness of those firms, and we think the more innovative these firms are, it will hopefully have a positive impact on their performance. And then there's environmental factors around it, the local demand conditions, the factor conditions, the government with their policies, economic policy might have an influence, and so for also local competition might also play a role. So you see, we can develop in our path model where we say, okay, we think the more innovative the firms are, the better for the firm performance will be. Firm performance might also be somehow related to all these environmental things, the factor conditions, whether there are supporting industries, suppliers, whether they are present, and so forth. And they might also affect the innovativeness, and by that they might have an indirect impact on the firm performance, right? Local demand might have an impact on innovativeness, but by that it might also have an impact on the firm performance, not just a direct path, but there might be also indirect paths. And the government, of course, what can the government do? They can somehow change locational conditions and by that hopefully stimulate innovativeness of the companies. So that was actually the basis, and what I then showed later on was somehow how we estimated the model. And in the end of this presentation, I will show the results for that model. At that time, when I presented it here at JIPS, I already said, actually, yeah, I noticed these people, the estimation method which I used were invented by Swedish people. And when I presented it here, I got more questions about the methodology than I got before at other places. So I thought that might be interesting. So apparently the people in my audience at that time were a bit more familiar with structural equation modeling than the typical audience or at other places. So now we list here a few examples. This is I just pick random, more or less randomly, some important Swedish innovations. The Celsius scale. When we are in Jönköping, we have to talk about the safety matches, right? Gustav Erik Klasch, and then actually I think that actually the first one was the inventor. He was a chemist from chemistry who found how they could be produced, the safety matches. And the second one, Johan Edvard Lundström, was an entrepreneur. He somehow made it the production of those safety matches here in Jönköping. He started the production actually here. Dynamite was also important. Child safety seat was also somewhat developed by a team of people, but according to Bertil Altmann. Also was surprised when I saw it because I thought this Tetra Pak might be a very, very recent innovation, but it's quite an old one. In the 1940s, it was already developed and produced and started. We have a very, of course, if we would look into IT, we would find many things. We would also, of course, we could talk about Ericsson, but Skype is also, there's a Swedish inventor behind it. Then we can also look whether it's an innovation, but I think that's also an innovation. Now I came to my talk here. I won't talk about those innovations, but I will talk about structural equation modeling. And that was the inventor in that case, but also the innovator was Carl Gustav Jørskog. So that is Carl Gustav Jørskog. When he got later on, he got prizes for his work. So this was some psychometric society in the US. He got a prize for his work. He was also honorary doctor I think in Jena, at the Jena University in Germany. Okay, now I want to talk about actually what is the difference between invention and innovation. I could have asked you what you think. Actually, I want also to ask you what do you think? What do all these Swedish innovation have? There's one common element in those which I showed you, but I think we need to skip this for the moment. So the invention, actually, what it's about the new idea, right? It's very typical that invention is, if it's in the technical field, it goes along with the patent. You might be able to get intellectual property right, exclusion rights for that. But what is the innovation? The innovation is more the application of a new idea. So we talk about innovation if it's something that it becomes really applied, and let's say economists or people in business management, they of course they think when it generates economic value. That is when you apply these things, when you produce things and sell them. Right? There's many patents which are never used. I mean, 2/3 of all the patents are never used. They have been invented, and then for some reason it's not. When they look at the costs and benefits, they see it would be too expensive to produce it. Some things are make it difficult to. The economic value is too low. We can also talk about different types of within the innovations. We have of course the process innovations. We have the product innovations. That's probably the first things you think about, but then also organizational innovations, like in logistics. You have many supply chain management. This is organizational innovations, very important. We have, sometimes we can also classify innovation as architectural, that you sometimes have in semiconductors industries, where you actually take existing technology and put them together and they define something new. Right? It's not the single components are not new, but the way how they are combined, they become new. Sometimes in society you might also have types of innovation in health system or something like that. Now, of course, when I looked at the work of Carl Jørskog, what I did, what the same was Charlie Carson very often does, he looks at Google Scholar. I did the same. Just to see is really, and if I say what is really important researcher or statistician. And that is what I found. So he has several papers with many citations in Google Scholar. So this, actually the first paper was related to factor analysis. Actually, somehow he showed a new way how to apply maximum likelihood estimation to factor analysis. Actually, that is, you can also later we will see path, if we have time, path dependence here. Because actually that was the basic for the further development of the Lisbon model. Being able to estimate latent variable models with maximum likelihood. So you got quite many citations for that. Okay, remember the citation is very field specific. In a way that you might find fields like in medicine. Of course, some people have many more citations because they are most cited work, right? I think for statistics, 1,000 is quite many. Where did he get the most citations? Later on, with some collaborator, Don Serbu, they developed the software. We'll later on talk about the software, the list. That is actually the innovation. They, of course, all the users, when they wrote a paper and use that software, they cite the manual. And therefore, for that they get 5,000 citations and so forth. Okay, let's say when in the scientific work, when he describes how it can be, how the model can be estimated, when he writes down the equations, of course, these are the type of the inventions, right? These are the new idea. They are not, at that moment, they are not implemented in something. Right? Maybe I could, you can just also notice the different journals. Okay, we have only 2 journals here, but this journal is called Biometric. It's actually a general statistics journal. Of course, it's a bit more, probably people in the biometrics are more attached to read this. And then it is also something in psychometrica, which is also a general statistics journal, but it's very often read by people working with statistical methods in psychology. Actually, there's another quite important paper which is published in the Journal of Marketing Research. So, by that, I don't think that it's somehow really a random choice of by. It was very clever to have it out in very different fields, so that the method become known in many very different areas. Actually, he started, I think, and just I think, I know we have some here from doctoral students in statistics, and I thought I need to show some equations, but very briefly, also given the time. We have, and that is the main equation, actually, the structural model, and attached to that, one thing I should mention is that the interesting, when I saw this the first time, the most interesting thing about it is it's formulated, so it looks, aside from these Greek letters which are there, like the first equation there, it looks apparently quite simple. It's only that these Greek letters are a bit scary. It's a linear function here. But the most interesting thing is that those variables formulated in the first equation are not observed. They are so-called latent variables, and that is really a bit fascinating, I think. We have a model in something which is not observed. How can that be estimated? Of course, in the end, something must be observed, because without any sample, without any observation, you can't estimate relationships. So that, and then for that, we need the so-called measurement models. I think I later on also have an example about this. Yeah, I don't think I need to go now into all these notational things in the detail. I just wonder, do I have 10? How many more minutes do I have? 30 minutes. Okay, that is not. That's all. It's more than I thought. I thought that I would have to finish at 10 o'clock. Okay, but things, even there are more things to come. Okay, what more should I? Then the assumptions are very standard. What you need for these types of models, like for independence of the error terms and the let's say, explanatory variables. Actually, most of you are familiar with simultaneous equation models. Actually, the first equation is also known in that area in a different way, with not latent variables but with observed variables. So there is some similarity here. And it turns also out that called Jönköping, he worked together with a famous academician who was very known for his work in simultaneous equation models, Arthur Goldsteiner. So then he transferred that knowledge here. This is now was the symbolic presentation, which of course is used when you have the lecture about structural equation modeling. This is more the intuitive way which you could use as a starting point when you talk about structural equation. What it is now, you see similar type of symbols here in this diagram. You see this the round circles showing the so-called the latent variables. Variables are not shown. You see the ethos, and you see the psi. Actually, the psi is the exogenous variable, and the ethos are the endogenous latent variables. So, and you see the different paths running. For instance, the psi1 is explaining both the eta 1 and the eta 2 here. And eta 2 is not explaining any other variable, so it's the finally explained variable, like in our example, the previous example, the firm performance, that could be. And then we might have innovativeness there. And then we have some extraordinary things here. And attached to those, there are the observed variables. We need some observed variables, otherwise we cannot estimate the relationship between those latent variables here. And you also see that is a very specific feature here, what you know from regression analysis. You have error terms here. So there's not, besides that, there's a linear relationship between the latent variables and the observed variables, the construct and the observed. There's also some random effects here, right? There's measurement error and so forth, which is very important because otherwise you would actually the statistical model comes in, right? When you assume there's some random element here. And show just another example. I showed you this is from a textbook here. When again you have different. This would be the size. The supervisor support the work environment and the co-workers, and those affect the job satisfaction, and in the end this affects the job search. So that would be the final dependent variable which you would want to explain. Of course, you can this can be observed directly, but in most cases you use several observed variables to attach those observed variables to the latent variables, somehow to measure that. Like environmental perceptions, you would have a question, you could send this questionnaire to people in an organization or in a company. I'm very comfortable with my work environment. The place is designed to help me to do my job better. There are a few obstacles, and what best describes the work environment. And then you can also have the same with job satisfaction, all things considered. I feel very satisfied when I think about my job. And how do they answer? This is the question. And then we'll have a scale below that question, which maybe goes from 1 to 5, it's a Likert scale, or from 1 to 7. And then the people can mark what they think about it. And which is the data that you have, and then you go back to that model and try to estimate those paths. Whether we find the depth on the co-workers, how some of these are evaluated, for instance, on the job satisfaction. You can see whether there is such a relationship, which is just to assume there is such a relationship, but from the data, hopefully, you can see whether you really can find it. Okay, now I want to go back. This was just another example of the path model, but what about Euroscoop? Why? Those of you who maybe have done some also work with of course they might have looked. Of course there were several people working in that area at the time. But why somehow became Euroscoop so successful in the end? He proposed the so-called the maximum likelihood approach to structural equation model, and also he developed the so-called, that I will skip, the software to estimate these type of models using maximum likelihood. And that was a very important thing because they became well, it's a different thing whether you have it on paper, whether you describe, or whether the people also can use it. And at that time, in the 1970s, of course, the people didn't have personal computers on their desk. It was rather complicated to estimate models. And to provide, and even, of course, there was very, very few software was available at that time. But maybe SAS wasn't available at that time, but it was very really difficult to use it. So they invented the method, how the equation, how it can be estimated, and then they implemented it into the developing a software, the so-called Listserv software for estimating these types of models. Actually, interestingly, the call was, at that time it was in Princeton, at the educational testing service or unit. And that one can see later on that this, the development of the list was very much related also to research and education. For instance, when we look at, for instance, intelligence, And then you have some different tests which are done and which factors are responsible for which tests the students get. Okay. I want a bit also to go back, because in the end it turned out that, of course, it's never so that one person is fully responsible for something which is done or invented or innovated. I think when we look at the history of Karl Joseph, we can see that many things are somehow have contributed to it. And apparently we talk a lot about Karl Joseph, but there is of course another one, is Dr. Serboom, who was a PhD student of Karl Joseph, and he was a very important. He's actually, when you read this, how he then later on described how he contributed, is he said he got the code from Karl Joseph for estimating Lissabon. When he looked at the code for a while, he decided it was best to review it from scratch. So actually, it was in the end, it was the doctoral student again who wrote all the code which was used in the Lisp software. But then the good thing was it started a long-lasting relationship or collaboration between those two. And then a very, I think, very clever move. There was a big market for those types of. At that time, I think in the US, they were ahead in using quantitative methods in all types of research, right? And of course, also the market is much bigger in the US. So what they did, they got in contact with software companies, scientific software, international, a US-based company, and they had a very good distribution channels to all the different professors at the US universities, and that they can could use some to marketing their program and to sell it to all these professors. Okay, that is somehow our Joseph himself thinking about what the factors. Of course, it was the Lisp remote. This type of approach was very interesting to several fields, not just to one field. And also, as I mentioned, he was very clever in publishing his papers in very different fields. So it was psychology, in education research, in business research, and also to some extent in economics. It was this type of already used. It went along with the development of computer technology. Of course, then it started that people got their PCs. And then they had the software that available which they could use themselves. And it was, of course, nowadays it wasn't really user-friendly, what we now with all the windows are clicking. But when they compared it to the mainframe things, like what they have used before, it was much better for the users to use it. And of course, they started to teach the structural equation modeling at the university, and became more users by that. Of course, they were also very active in that field. What is it? Why did it not? I will just show something. How did it? Of course, it was a very good background in mathematics. Actually, interestingly, he didn't want to become a professor or a researcher. He wanted to become a teacher at school. And just by some randomness, he got a phone call from Hermann whether he was looking for research assistant, and then he got the job. And Hermann would also require that he started mathematics and physics, but he demanded that he would also study statistics. And then, as was demanded, he did so. And he was he must have been a very good student, because just in 2-3 years, he started the first studies in mathematics and physics, but even the statistics, he started in 1 or 2 years, he got the master's degree, and 3 years later, or not, 2 years later from the master's degree, he got a statistics degree. Right, so that is really a tough job for the doctor in such a short time. And then maybe that was also very influential. He spent 7 years abroad in the US as a postdoc. But also interestingly, at that time, he got we don't know how we can call him, but he got an invitation from his previous supervisor. At that time, it was Vicanos at Summer University, to return to Uppsala or to become a full professor of statistics at Uppsala University. And so he, and then all throughout his career he stayed there. And he became, I think he's still to some extent active, but he became professor emeritus in 2000 at the age of 65. So that is, I have previously the picture of, this is the Hermann. I think some here in this audience have met, because the Hermann Bolt was also in Gothenburg, professor in statistics for some time. But I think must be before the Uppsala time, right? He was in, I don't know, but that is nothing. But why do I show this? Actually, I think some of the influence of the doctoral supervisor and how the interest of the doctoral students develop is very important. What I also want, if you would go into detail, I have something to show you on that. Yeah, I have it. So Hermann Bolt did his own way of structural equation model estimation. He proposed the so-called method partially squares. And actually that method has become now much more popular in recent times. Why? Because in recent times there is no software to estimate it. It's very different philosophies which are behind it, very different assumptions. This is called soft model. There's almost no distribution assumption here. It is not a really statistical technique here. This has very strong assumptions, like the multivariate normal distribution of the observed variables. Therefore, by that, it requires huge data sets, which you can use PLS with very small data sets and the force. But this was never really successful, this method, because before bootstrapping became available, you couldn't do any tests in this PLS framework. And now for most research, they want to test something when they have estimated the path. So, and then for 20 years, it was not really noticed that there is like something like PLS. But literally from the beginning, it was very popular, became very, very popular. Now, I already mentioned that the PLS is something which is now around. I think more and more people use the PLS for some reason. Which has more data or distribution assumptions appear to be very strong. They use this PLS. Of course, in the meantime, there are, of course, you can't protect these the type of estimation method. This is, let's say, scientific knowledge, and of course, others can copy it. And they have copied it, and they use it in other software packages like ARMOS and SPSS, S1, EQS, Tetrat. And there's also, of course, in R, there's also another, the Fox R package, which can also estimate those ones. When you ask me about the future development, there's something new now coming up. I just recently observed it. It's called generalized structured component model, which is something interesting. It's the compromise between PLS and distance. I think that will be the future in structural equation models. It's I think it's Corinne, which he's in the US now. If they succeed in developing a software, because even if it's written on paper, if the people that can use it, they won't use it and it will not be acknowledged as a good some improvement with regard to PLS and this. Finally, I want to show you our results, what we got for our model on the locational advantage, if there's any. So some things are, the good message here is we got actually the more innovative the firms are, the better is the performance. But then we also get some conflicting results. So Porter is, at least we can't really use Porter. We find if there's local rivalries or local competition, if there comes out there's strong local competition, we see it has negative effect on the performance. And even this might be not that surprising, but the local demand. If they say they are locally somehow have strong local linkages with suppliers or with our customers, we don't see that they are performing better. Unfortunately, they're performing worse. But it's the other side of the medal. But the more successful you are, the more likely it is that you become an exporter, right? So by that we can explain this negative result. My final reflection is about cross DC, and as I mentioned, I forgot to mention some things, but the interesting thing is also that he already started in his master's thesis to do some research about factor analysis. So, and then he got into this environment of Hermann Wald. He was interested in path analysis. And that he got an employment in educational training center at Princeton University, which were also interested, had many data sets and so forth. So that was, there is somehow a history behind it. Here you can also see that some people in the professional are also very good in marketing the things which they are developed, right? They produce something which is, I found no information about royalties or what he got for his giving this code to the software, but I think there must be something like when you write a book, you will get something for it. And also he taught the courses, the SEM course, and for that they charge fees. Then the productive life cycle of it. If you look, when do you think was the most, all these famous papers which are so heavily cited, they were in the very early stage of the career. And of course, they are also serious about it, because actually the returns of that is much better if it's done early. And on the other hand, you can also, of course, maybe the younger researchers have better ideas. And if you would look at Nobel Prize winners, most of those things are done at very, very early stages, around 30. They have their, and they're probably they're not really thinking in those. The longer you are thinking about things, you become more and more. You have the way of how to think about that. But when you're young, you have more ideas, right? You want also to do things different, how they have been done previously. And that is probably more difficult when you become older. The environment, of course, is very important. Also, the interest in what you are doing. And I think we could say the collaboration is not the single inventor which is behind it. He met very important, like I mentioned, Arthur Goldberger, and he met his doctoral advisor, Hermann Wald. He met other important people who contributed to Doug Serban. So which developed the code for the software. Of course, that without those surrounding elements, probably we would never have seen this trend coming up. And then when I looked at that and noticed how many things were in my first slide, actually when he focused on the factor analysis and structural equation through his whole career. So I think maybe that is something to do to dealing with one topic, and of course there's also learning curve, and then we can become really the guru in that field, right? If you do only the one thing all the time, but that might be also boring in the long run. I don't know. Okay, so that's now I'm at the end, and hopefully there's a few more.
So now I want to thank Andreas Stephan for giving us this lecture. Thank you very much.
Yeah. Thanks.
Thank you.
Yeah.